All right, we have a media representative down at Kennedy Space Center in Florida. You're on, go ahead.
Yes, Dan Billow from WESH-TV. I wanted to just hear a little bit more about, I didn't quite catch some of the details of the exoplanet, the large planet that you're kind of looking at. Tell me one more time how close that is to its sun and more about its temperature, if you can, in Fahrenheit.
Well, the distance is about 0.04 AU. That is to say it's about 1/25th the distance from the Earth to our sun. So it's very, very close. The temperature is something people are trying to understand right now, but estimates come up between 2,600 degrees Kelvin and 2,700. A degree Kelvin is almost 2 degrees Fahrenheit. So we're talking about temperatures like 5,000 degrees Fahrenheit.
All right, I believe we have a call from Ames now.
Hi, this is Matt Bigler, KCBS San Francisco. The question is, give us some perspective on all this. I think there's a lot of scientific information that is hard for some people to understand. How big a deal is this? What does this mean in terms of the long-term pursuit to find out if we're alone in the universe?
Bill, you want to address that first?
Sure, I'd be happy to address that. This is a step along the way. When you think about what we're doing, it's been preceded by other steps. Michel Mayor, his people at Geneva, Switzerland, the Corot people, all these groups have made a step trying to help us understand what's out there. How many planets are there? What sizes are there? What kinds of stars do they orbit? Kepler is a more competent spacecraft. It's got a bigger aperture. It can look at more stars. It can find smaller planets. But it's a step along the way. It determines the frequency of Earth-sized planets. But what Alan talked about later, a moment ago, in fact, was that there's a step beyond that. We want to find, after we found these planets, what's in their atmospheres. Which stars that are close to us have planets. And there's steps beyond that, steps that our probably our children will take, where they ask, we want to, maybe want to send a probe to those stars. I'm not sure what will happen, but this is just a step along the way in mankind's exploration of the galaxy to find out whether there's other life out there.
Could I add to that too, please? As Bill says, Kepler is basically going to tell us if Earths are there and how many there are, and that's a very important point for planning that next generation of space telescopes. You don't really want to build an even bigger space telescope if you're not relatively certain that what you're going to search for is there to be found. In the Discovery Space plot that I showed earlier on, there are hints from the ground-based surveys, which can't really find Earths yet, but the so-called super-Earths, the hot and the cold super-Earths that have been found so far, they are actually enormously common. The estimates are that something like 30% of sun-like stars have these more massive versions of the Earth, though none have been found to be truly habitable. Some of them are close to being habitable, and so just based on that statistic alone, we think that it's most likely that Kepler is going to find just oodles and oodles of Earths. Some of them are going to be too hot, some of them will be too cold, but some will be like Goldilocks, just in the right place. So that's Kepler's huge contribution, is it's doing the sanity check and making sure that we're ready for the next generation and perhaps even helping us plan for the next generation.
I just have one short thing to add. That is, I hope we'll be here 3.5 years from now giving you the answer of how common Earths are in our galaxy.
And in summary, then, the news we're providing is that Kepler works, as Alan and everyone pointed out. And it can make the measurements it was designed to make to see an Earth-sized planet move in front of a Sun-type star with an Earth-class orbit. And so that's the update we're bringing you now. But in addition, we're also finding some new science out about this other transiting object, which we already knew was there, but now we're able to highlight the performance of Kepler and learn new physics about yet another class of planets out there. So, J.D.?
Good. We're going to go to a telephone bridge now with Dan Vergano at USA Today.
Thanks very much. I was wondering if you could elaborate on that. I'm afraid I'm getting echo on this call line. Are you going to be getting any atmospheric information from those Earth-sized planets that you eventually detect?
The Kepler stars are quite distant, and we will not be able to get atmosphere information from the Kepler Earths. It's a matter of, which tool do you have for which problem. Kepler is now basically the best way to find Earths at all. But just for the design of that particular experiment, in order to count how many Earths there are, you have to have a lot of stars in your field. And to have a lot of stars in your field of view, they just have to all be far away. So we won't be able to follow up on those ones. That said, we hope that, again, repeating what Alan said earlier, that Kepler would tell us how common Earths are, and that will enable us to do new experiments where we can look at brighter stars that are closer to Earth, where we are able to do the follow-up measurements. And I have one more thing to say that's kind of tangential, but because it's going to take so long to find an Earth where we can study the atmosphere, there's a sort of separate line of exoplanet science going on where people are looking for transits, a planet transiting a star, a bright star, but not a sun-like star, not an Earth-like planet. This would be a big Earth orbiting a very, very small star. So there could be other news in the next few years. It's not related to Kepler, but to these kind of different kind of Earths, not true Earth twins, but other kinds of stars where we may be able to follow up their atmospheres in the future with a telescope like the James Webb. But for Kepler, we won't follow those particular Earth-sized exoplanet atmospheres. They're too small and too faint.
Yeah, to follow up on that, as Sarah says, the so-called hot super-Earths may very well have an awful lot of emitted light of their own, as well as the reflected light at optical wavelengths, if they really are hot enough. So they will have something perhaps looking like the HAT P7b light curve. But by looking for Earths, which we don't want to be that hot, we don't want to be living on a planet that's so hot that it's glowing red. We want to have a nice habitable world. By definition, that means that that planet is not going to be emitting that much infrared wavelength. It's just going to be giving off optical light. So we won't have these beautiful rise and fall that we saw with HAT P7b. So we won't be able to learn directly about the atmosphere, or at least atmospheric temperatures, in the same way we can by studying hot Jupiters or hot super-Earths.
All right, we're going to go back to the telephone bridge with David Perlman from the San Francisco Chronicle.
Oh, hi. Thanks for taking the call. What will it take? And I guess this is, again, we're hearing a lot of echo, but I'll try to break through. For Bill Marucki, Bill, what will it take to, as the next step, which would be to analyze the atmosphere of any Earth-like planets that Kepler finds? Does it require another generation of space telescopes? Would the James Webb be able to do it? What will it take?
That question is actually better answered by either John or Alan. John?
Sure. Alan might be able to talk a little more quantitatively, but a lot of things in astronomy are about aperture, and James Webb is going to give us in space access to wavelengths we can't observe on the ground that can give us diagnostic information, and also have the largest collecting area by far of any space telescope that we've flown. And there is a study group looking at what sort of exoplanets James Webb would be able to study. And Alan, I don't know if you're on that working group, but I suspect you probably interact with them.
Well, I can make some more comments, which is that it's going to be, I think, almost impossible to do a follow-up of the type we would like for the typical Kepler planet, because it's typically going to be at several thousand light years away. So that's like a factor of 100 times farther away than the closest Earths that we'll find eventually. And that factor of 100 counts, because the problem is that we're not so much trying to find something really faint, although a planet is no fainter than, say, a 25th magnitude galaxy, the sort that the Hubble Deep Field can take a picture of. The problem is you have this faint planet next to a very bright star. So it's a question of being able to resolve something faint next to something very bright. It's like looking for a firefly next to a spotlight that's pointed in your eye. And as you're 100 times farther away, that problem trying to resolve this faint object next to the bright object gets 100 times worse. So by definition, our best chances for finding Earths and studying their atmospheres are going to be the close-in Earths. And even then, it's tough enough to be able to resolve something which is at optical wavelengths 1 billion times fainter than the star, or at infrared wavelengths 1 million times fainter. So for Kepler, Kepler is going to give us the sanity test, the proof that Earths do exist, and that will give us the motivation to go ahead and find the nearby Earths where we really can study their atmospheres by a variety of either optical or infrared telescopes.
I'll add one more thing, and that is to look at the atmosphere